Hello and welcome to Micromaterials. I'm Andy Bird, and in today's video we will review application examples of the micro impact capability of the NanoTest, highlighting analysis features and providing an insight into what this unique test can offer. The impact module on the NanoTest takes advantage of the pendulum-based load heads, both low load and high load, to deliver a high energy impact concentrated into a tiny near surface sample volume, making it highly sensitive to coating properties at very high strain rates. Nano and micro impact can be used to compare the toughness and fatigue fracture resistance of thin films and coatings, as well as bulk materials. As we will see from the case studies presented in this video, application areas that can benefit from this small-scale impact test include PVD hard coatings, ceramics, thermal barrier coatings, and much more. User-definable test parameters include accelerating force and distance, number of impact cycles, impact angle, and impact frequency. Typically, cube corner indenters are used for nano impact, and small radius spheroconical probes are used for micro impact. Impact tests can also be performed up to 850 degrees Celsius with the NanoTest Vantage for characterisation at relevant in-service conditions. In our first example, cyclic micro impacts were performed on multi-layered PVD coatings on tool steel with a 20 micron end radius diamond spheroconical indenter. So let's take a closer look at the output from a 500 millinewton 500 cycle test. This plot shows the probe displacement and velocity data for the first impact, or pulse as it's referred to in the software. On the x-axis we have time from 0 to 0.075 seconds. On the left-hand y-axis we have the depth or indented displacement throughout the impact, and on the right-hand y-axis we have the indenter velocity, which is the blue line as we can see here. We have two plots for the displacement, raw depth and analysed depth. The analysed depth adjusts the initial sample surface position, i.e. the zero depth point, based on the assumption that the indenter touches the surface at the point of maximum velocity. The NanoTest software is able to extract various analysis parameters, as we can see here. Firstly, we need to ensure that the correct area function is used. In this case, we have a 20 micron radius spherical indenter. So now we have the corresponding analysis values, including V in, which is the maximum velocity of the indenter at the point of impact, V out, the maximum rebound velocity, dissipated energy, which is a percentage ratio of the velocity in to the velocity out, various measures of depth, including maximum depth, residual depth, and contact depth, contact time, which is the total time the indenter is in contact with the sample during an individual pulse, and equivalent force. This is derived from the accelerating force, in this case 500 millinewtons, and the effective mass of the load head. With these parameters, we can calculate dynamic hardness or high strain rate hardness, defined as energy imparted divided by volume of the imprint. These analysis results relate to just the first pulse, and this is a 500 cycle test, so we have 500 pulses all in the same location on the sample. By clicking on Next, we can review the analysis for all the subsequent impacts. What is more useful, however, is to plot out some of these parameters as a function of number of impacts. We can do this by going to View, Analysis Results Plot. Now we can see the total maximum depth of the indenter as a function of the number of impacts, or pulse number. So clearly we have some initial deformation followed by this long fatigue period, and then coating failure as indicated by this sudden sharp increase in depth. So there are several other parameters that we can plot, as you can see here. Dissipated energy is a particularly useful one, so let's go ahead and add this to our second axis. So we can change the scale of any of these axes just by typing in a number here. So we put that to 100, space that out a bit. So it gives us a nicer view of these two parameters. So we can see a sudden jump in the dissipated energy that occurs at the same time as the increase in depth. This increase in dissipated energy is caused by coating failure, i.e. energy is lost as coating cracks and fractures. Replicating this test on other coatings allows for a direct comparison of high strain rate fatigue resistance, as shown in this plot where we have several coatings of different compositions. From this data we can generate SN fatigue curves, as shown in the example for the 3 titanium nitride based coatings with different microstructures here. In this case we have plotted applied load on the y-axis, but this could be converted to energy if required. In summary, the cyclic impact test provides a fast quantitative method for ranking the performance of hard wear-resistant coatings at relevant high strain rate conditions. This technique has demonstrated direct correlation with coating performance in macro-scale cutting tests. In our first example, we looked at multiple impacts in the same location of the sample surface. By spatially distributing impacts across a small defined region of the sample, we can directly study how damage from one impact affects subsequent impacts. This allows for simulation of impacts in a methodology more similar to erosion, where particles impart energy across an area. When setting up a randomized impact test, there are 2 distribution methods we can use. Firstly, we have Gaussian, as shown here on the left, in which impact locations are randomly spaced but tend towards the center of the user-defined area, as described by a Gaussian distribution. Secondly, we can have a rectangular distribution, as shown on the right, in which impacts are randomly spaced in the XY axes across the whole area. Note that the boxes in both these plots indicate the maximum extent of the impacts as defined by the user. 150 by 150 microns for the Gaussian distribution on the left, and 200 by 200 microns for the rectangular distribution on the right. The distribution used depends on the type of erosion or particle damage that the user is trying to replicate. The example shows 4 tests, 50, 150, 250 and 500 impacts on 2 glasses, fused silica and BK7, using a 20 micron diamond conical indenter. The impacts are positioned in a rectangular distribution across a 1 mm square area. Note that to ensure a fair comparison between samples, the impact locations are the same when comparing a test on one sample to the other. Clear differences can be observed, with the BK7 exhibiting more extensive damage. This is caused by differences in crack systems due to different microstructures and mechanical properties. Similarly, distributed impact tests on bulk ceramics show marked differences in damage tolerance. In the example shown here, 500 mm distributed impact tests were performed over a 300 by 300 micron area on alumina, magnesium oxide partially stabilized zirconia and sapphire. The partially stabilized zirconia performed slightly better than the alumina, with sapphire being significantly worse. This behaviour is consistent with differences in erosion rate reported in literature. In addition to randomized distributions, experiments with controlled spacing between impacts can be performed, such as the test shown here on the 3 ceramics. These tests indicate that sapphire has higher interaction spacing limit, so cracks form and coalesce more readily between impacts further apart than on the other ceramics. The spatially distributed micro-impact test is becoming a particularly useful tool for the development of thermal barrier coatings due to its ability to quantitatively simulate erosion on a small scale. In this example, a 175 micron thick gadolinium zirconate thermal barrier coating was subject to distributed impact tests using the NanoTest. The compaction and cracking at crater peripheries exhibits strong similarities with the damage caused during an erosion test with angular alumina as the abrasive media. Here we have 2 distributed impact tests over a 500 by 500 micron area. Left is a Gaussian distribution, and on the right a rectangular distribution. The red dashed areas in the images show areas of significant material removal. What is noticeable, particularly in the rectangular distribution test, is that material removal occurs in an area with relatively low impact density. This indicates that cracks are forming and propagating across several columns of the thermal barrier coating, facilitating material removal. Cross-sectional SEM imaging of the samples confirms this. On the left we can see cracks propagating in the yellow circle and areas of material removal, circled in red, as a result of the distributed impact test. This very closely replicates damage mechanisms observed from the erosion test as seen on the right. Nano and micro impact testing is proving to be a powerful tool for the characterisation of thin films and coatings at very high strain rates and energy densities. I hope this short applications review video has given you a useful insight into the capabilities of cyclic and distributed impact testing, as well as illustrating how it can be used for materials development, particularly in the fields of cutting tool coatings and thermal barrier coatings. You can find out more about equipment capabilities with the provided links to Micromaterials technical notes. Thank you all for watching this application review video from Micromaterials, and we'll see you again next time.